I'd like to go this.
Hey Tyler, how are you?
Good.
Good.
So it looks like we're back to combustion.
Yeah, well, so in class today we did two different activities. One was on heats of formation and using those to calculate enthalpy for a reaction, and the other was on Hess's law. And I think Hess's law is maybe a little bit trickier, and so I thought we'd start off with doing an example of Hess's law that's maybe a little more complicated than the ones in the activity. And the reason why I like Hess's law is that it's like a puzzle, and it requires kind of logical, careful thinking, and so it really works on critical thinking skills, which are one of the things, hopefully, that we all develop as we learn.
Sure.
Right, and so here we have our target reaction. Graphite reacts with hydrogen to make C3H8, which is propane. And we don't know what that reaction, the enthalpy for that reaction is, but we do know the enthalpies for these three reactions.
All right.
And some of the molecules up there appear down here, and some of them don't. And so we have to try to figure out how are we going to arrange these so that they can add up to that reaction up on the top.
Okay, so these are the pieces to the puzzle.
These are the pieces to the puzzle, and when we're done, it's going to look like that.
That's
and
a picture on the box.
Fill in that little space up there.
Right.
Okay, so I'm going to draw a big line across and say,
Great line.
we're going to, great line, right. Okay, so how do we do this? What do we do? What do we look for?
So let's start by looking at the product.
Okay, so we focus on molecules up in the target reaction and look, where do they appear down here? Are they on the right side or the wrong side? Do they have the right coefficients or the wrong coefficients?
Right.
And so we'll start with the most complicated molecule up here, propane, C3H8. It appears as product. Where does it appear in our pieces?
It appears here in this first reaction, but it's on the wrong side. It's on the reactant side as opposed to the product side.
Right, so on the reactant side, and so I need to flip that reaction backwards, and then when I flip the reaction backwards, I change the sign of the enthalpy. Okay, so now we know we've used this one, we're not going to be able to use it again, and so I cross it off. Okay, what's next? Well, let's go with this. How is this related to what's up there?
Well, it's on the correct side, but here we see that there's no coefficient in front of the carbon, whereas up there, there's a 3.
Yeah, so we're looking just at the graphite. Appears on the reactant side, so it's good, but the wrong coefficient, and so I'm going to multiply this by 3.
So that it matches the end puzzle.
Exactly. And when I do that, I have to multiply all of them by 3. And in fact, multiply this by 3. Okay, so I'm going to write that now, the result down here. Okay? So now we're done with that second reaction. I've used it. I can't use it again.
Right, and we have to make sure that we keep that negative sign because it's going to be important later.
Exactly. You only switch the sign, get rid of the negative, if you flip it backwards. Okay, now we're down to our last one, and hydrogen. Well, it's a reactant here. What's it up there?
Reactant, so it's on the right side.
On the right side, but it's only got a coefficient of 1 here, coefficient of 4 up there. So I multiply this by 4, have to multiply that by 4, multiply that by 4, and that by 4.
Right.
Okay. Okay, so now we have that equation written down with 4 times its energy. And the last step is we add them all together, right? I add this plus this plus this. That's going to give me the balanced overall equation. I take this plus this plus this. That's going to give me the overall energy. What do you think?
Well, this looks okay. I mean, we have, so you took 2,219.9 and subtracted these two things from it.
Yep.
And we ended up with, okay, one number, that's good, but this just, it's a lot of pieces left.
Yeah, it's a lot of stuff. There was just adding everything on the reactant side, everything on the product side. I left off the states of matter to save space, a little crowded. And the last step is to cancel things that are exactly the same on opposite sides, and then also combine things that are the same on the same side. So for example,
Let's cancel this water here.
okay, So you have
Okay,
4
so I
waters.
have 4 waters.
I have 4 waters.
Okay.
How about the CO2s?
I have 3.
I got 3.
Alright, it's like my Go Fish.
It is.
Alright. I have 5 O2s. How much do you have, Dr. Godez?
Well, I have 3 and 2. I guess that's
So you do have a
5.
7. Alright.
Okay.
Great.
And what are we left with?
But now I'm done. I can't take anything else out or I'd take away the product.
Yeah, and I think everything is unique now, right? I have the 3 carbons from the graphite, 4 H2s, and that goes to the C3H8.
Which is exactly what we see up there if we take all this canceled stuff out.
Yep. So it worked out.
So we have the answer here to the question that was above.
Great. Well, good job.
Way to put together the puzzle.
Easy peasy. So the other thing we did was using delta H formation values. And so here I have reaction. It looks somewhat familiar. And the idea for using delta H formation values is there's this equation that if we know heats of formation, you take all the heats of formation of the products minus all the heats of formation of the reactants, and you get the overall reaction. So the first thing we have to do is get heats of formation. Where are we going to get those from?
Table.
Yeah, we get them from a table. They have to be something that somebody else measured. Right. And the textbook has an appendix in the back, thermochemical data. One of the columns is delta H formation. And so we're going to look those up, and we'll write them down to start the problem. Okay, and so these are just the values that were from that table in the back. And the only thing I really need to remember is that it's products minus reactants, and I have to keep account of the coefficients, right? This is for 1 mole of CO2. Well, the Bound's equation has 3 moles, so I have to multiply that by 3 in the equation. And so to get delta H formation, or delta H for the reaction, it's the products. So that's the products minus the reactants. And we only have 1 reactant. Remember, elements, heat of formation 0, 1 reactant, coefficient's 1, so that's actually easy. So minus, and these are all kilojoules. I should be a little more careful and write it with each quantity, but to save space, I'll just put it at the end. And so when we calculate that all out, we get a number, negative 2,219.9 kilojoules. And one of the weird things is that it's a molar quantity. That's that many kilojoules for 1 mole of C3H8. That many kilojoules for 5 moles of O2, right? Because they're tied together.
So it's for the reaction.
It's for the reaction as written. Okay? So again, remember products minus reactants, and make sure to take into account the coefficients in the equation.
All right.
Great.